Assalamu alaikum, I'm Farishta Kabir and today we are going to discuss about the Generative Adversarial Networks or GAN. First of all, we need to understand what is GAN. Generative Adversarial Networks or GANs are an exciting recent innovation in machine learning. GANs are generative models. They create new data instances that resemble your training data. GANs were introduced in a paper by Ian Goodfellow and other researchers at the University of Montreal in 2014. Facebook's AI research director Ian LeCun called adversarial training the most interesting idea in the last 10 years in ML. Let us understand the models first to get into the background of GAN. There are usually two kinds of models, generative models that can generate new data instances and discriminative models that can discriminate between different kinds of data instances. The generative models generate new outputs based on its trained data, and discriminative models distinguish based on labeled data and their categories. While generative models capture the joint probability, discriminative models capture conditional probability. A generative adversarial network or GAN has two parts. The generator that learns to generate plausible data. The generated instances become negative training examples for the discriminator. Then the discriminator learns to distinguish the generator's fake data from real data. The discriminator penalizes the generator for producing impossible results. Generator training requires tighter integration between the generator and the discriminator. Then, discriminator training requires. The discriminator training data comes from two sources. Real data instances such as real pictures of people. The discriminator uses these instances as positive examples during training. And fake data instances created by the generator. The discriminator uses these instances as negative examples during training. This is the entire structural overview of a vanilla GAN model. Here is an example of the GAN structure. In the example, as we can see, the actual dataset was real wines, and the generator is producing fake wine samples and adding up with the real ones, whereas the discriminator is distinguishes among those data to determine which samples are real and which are fake. Because a GAN contains two separately trained networks, its training algorithm must address two complications. The first one is GANs must juggle two different kinds of training. The second one is GAN convergence is hard to identify. The GAN training proceeds in alternative periods. The discriminator trains for one or more epochs. The generator trains for one or more epochs. Repeat step 1 and 2 to continue to train the generator and discriminator networks. Then comes the loss functions. The most common types are minimax loss and Weierstein loss. In the minimax loss function, the generator tries to minimize the following function while the discriminator tries to maximize it. Then comes the Weierstein GAN loss function that depends on a modification of the GAN scheme called Weierstein GAN or WGAN, in which the discriminator does not actually classify instances. For each instance, it outputs a number. There are many types of GAN architectures, such as cycle GAN, style GAN, pixel RNN, text-to-image, disco GAN, ISGAN. The application area is extremely vast for GANs, such as generating examples for image datasets, photographs of human faces, cartoon characters, image-to-image translation, text-to-image translation, etc. For example, here we can see realistic human faces are being generated and none of these people really exist in real life. This is also used for deepfake creation. Then comes the living portrait that has given life back to Mona Lisa by creating moving expressions on her face. Many animators now prefer using GAN for their character creation. Who knows, maybe one of your favorite characters is created with GAN too. There are other uses also, like super resolution and text-to-image translation. Here comes the limitations. First of all, the structural limitations, like vanishing gradients, failure to converge, mode collapse, and inversion is not straightforward. Then comes the implementational drawbacks, like inability to invent totally new outputs, complicated to handle, and negative usage, such as fraud, scam, and fake news. Over a few years, applications of the generative adversarial networks, or GANs, have seen astounding growth. The technique has been successfully used for high-fidelity natural image synthesis, data augmentation tasks, improving image compressions, and more. From emoting super-realistic expressions to exploring deep space, and from bridging the human-machine empathetic disconnect to introducing new art forms, GANs have it all covered. That was all from my side about generative adversarial networks. Thank you so much.